Hello.
Hello, everyone. Uh, Hello, and welcome to the latest webinar in the AI for Net Zero series. My name is Amin Zarei. I am research fellow at the University of Surrey. It's my pleasure to chair this session, which is dedicated to early career researchers working under umbrella of AI Artificial for Net Zero, that is funded by UKRI. Um, today, today we are thrilled to host two excellent speakers, Dr. Isabella Fumarola, if I say right, from Imperial College, and Dr. Meshkat Dolat from University of Surrey. Please join me welcoming them. I highly encourage you to participate in the discussion by sharing your comments and questions in the chat box. We also have a 10-minute Q&A session at the end of each talk, giving you the opportunity to engage with the speakers directly. Just quick reminder to leave your comments and ask questions. Please ensure you log in into your Google account. So before going to first presentation, I'm delighted to introduce Professor Ahmed Al-Sheikh, who is co-chairing today's session with me. Thank you for joining, Ahmed.
Thank you for the introduction.
And without any delay, let's introduce our first speaker, Dr. Isabella Fumarola, if I say correctly. A quick introduction for her. She is a research fellow in the Department of Aeronautics at Imperial College London. She has been in Imperial since 2020, previously as a research associate working on experimental aerodynamics. She holds a PhD from City University of London. Her main research topic is finding flow control techniques to reduce drag in either turbulent boundary layer or bluff body weights. She works for AI for Net Zero project, leading experimental campaign in wind tunnel in a scale model. Today, she has a presentation on the title of the role of experiments in the development of the novel AI-based technology to achieve net zero. So thank you for joining, Isabella, and the floor is yours.
Thank you. Thank you for the opportunity of giving this talk again. So as you mentioned, I come from a slightly different background from AI. I'm an experimental aerodynamicist, so I work in wind tunnels. And today I'm going to present this work that we're doing here at Imperial within AI for Net Zero. And I hope to give you a panoramic of what experiments how experiments can help the development of AI-based technology to achieve net zero. So obviously this comes from the problem of climate change and trying to reduce emission, and we want to optimize energy efficiency in energy and transport, and to achieve to achieve a better technological solution. And the idea is obviously AI and has a lot of technologies and now are available to different applications. Here are some example of power wind turbine, truck or plane. And the idea is how can we make this theory applicable to real life solution. And obviously what is the missing point to make this real is an experiment of proof of concept. But experiments don't come with, obviously come with a lot of challenges. First of all, we need to simulate realistic flow condition, realistic condition in general. And for this, we need cutting edge facilities. We need the multidisciplinary knowledge to carry out any type of experiment. They are expensive and time limited. And what I really want to show today is which are the different elements that build up the experiment to then eventually make the solution real. I said I'm an experimental aerodynamicist, and the first question that can come to mind is why do we need the aerodynamics? And obviously, if you look at all these applications, whether they are transport or energy source, the common characteristic is that all these systems work in a fluid flow. That can be air, or if we start thinking about ship and submarines, can also be water. And often when you want to go closer to the realistic condition, having a numerical simulation of complex geometry as complex flow is not always feasible. More specifically, the project we are working with in AI for Net Zero is focused on heavy road vehicles aerodynamics. And the main motivation is that if we look at the greenhouse gases emission, this is 2003 in the UK, what we can notice is that about 35% of the total emission are due to heavy road vehicles and light-duty trucks. And we can also imagine just by looking at the amount of time we order something online, how long it takes, like how many trucks and vans are bringing goods to our houses, how this topic becomes quite important. And more specifically, if we consider the 50% of the power from an engine of a truck, that is used to overcome the aerodynamic drag. So the aerodynamics plays quite an important role in this problem. If we reduce like drag by 10%, we can estimate that the fuel consumption will be reduced by 5%, just to give an idea. So if we look at the flow around a truck, like the one here on the bottom side of my slide, we can see that there are a lot of areas, gaps, and the flow under the vehicle. That is where the flow becomes more detached from the vehicle itself, and it dissipates more energy. But in particular, 25% of the aerodynamic drag comes from the wake. And this is the reason why we mainly focused on the wake. In addition to that, you can see that there are a lot of devices like the fairing on top of the front of the vehicle, or this skirting, next to the wheel that have already been implemented to improve the aerodynamics of the truck. So what is the state of the art? Commonly, this type of vehicle are seen more in US, I've been told, than in Europe, but solution that are actually implemented include static flap or boat tail, and these are static solution that tends to streamline the flow around the vehicle. But the question is, can we actually do more? And can we do more by controlling the unsteadiness in the wake? Because if you think about fluid dynamics, obviously the flow is very chaotic and is moving and is creating all these like little structure that are moving around, and they're responsible of dissipated energy. So can we improve the current solution by moving the flap? And how can we optimize this movement? Well, what we're doing is that we are looking into applying a reinforcement learning algorithm that can control the movement of the flap via feedback from some sensors that are on the rear of the vehicle. So I mentioned we do this experimental. So the next few slides will explain how we built up our experiment, what's needed, and then I will move to some preliminary result to give an idea of what this project is going. So the first element for an experiment is obviously the model. So we use a scale track 1 to 14 because we wanted to, as I mentioned, a realistic geometry. We then equipped our model with some sensor. You can see here the hole for the pressure taps on the rear, and we also equipped with 4 flaps that are moved with gimbal's motor that you can kind of see in this video. We have also a load cell that is capable of measuring the drag force and the 3 forces and 3 momenta directly. And then obviously we need the wind tunnel because we're talking about aerodynamics. And this is our 10x5 wind tunnel at Imperial College. If you want to know more or you are interested in wind tunnels in particular, this is part of the National Wind Tunnel Facility. There's the link here on the bottom. It has two test sections, one on the lower part and one on the upper side. The one on the upper side is quite big. It's like 5 meters by 2.9, up 18 meters long, and it can reach up to 11 meters per second. The one on the lower is a bit smaller in section, but it reaches 20 meters per second, but it is equipped with a rolling road. So our truck has been placed in the lower test section, and the rolling road is one of these elements that are needed to reproduce real life conditions. So if we look at a truck moving on a steady road in a steady air, what happens is that obviously the truck is moving at a certain speed, the road is not moving, and the air is still. When we move to the wind tunnel, we have a bit, the reference system is changing because the truck is stationary, but the wind is actually blowing against the truck. And in this case, if we want to replicate the effect of the road, which is normally called ground effect, we have obviously to move the ground, and this is what we can do in our wind tunnel. Another aspect quite important is what happens if the truck is driving on a road with wind. So it's not there, it's not still anymore, and what happens is that the wind can come from any direction. This one, for example. In this case, what you have is what normally we refer to as the yaw condition, in which the component of the direction of travel is different than the direction of the wind. And so what we can do is that we can turn the model by a certain degree, and we can replicate exactly the same condition in our wind tunnel. Another aspect is obviously measurement techniques. I mentioned pressure, I mentioned forces, but when we want to investigate the flow field in the wake, and we want to understand the flow physics, what we are interested in is measuring the velocity in the wake, in time and space. And this is one of the examples of the measurements technique we used, which is a volumetric particle tracking velocimetry. So what we do is that you fill up some soap bubble with helium, so they're quite light. And when you are in the wind tunnel, they will follow the wake or the flow around your body, in this case the truck. And then we mount 4 cameras, and the 4 cameras are looking at this volume and are capturing images in time. They are like high-speed cameras. And what you end up having is a number of particles that are moving around, and they, at first look, they may look chaotic, but you can see some of the vortices. And when you analyze all these particles in your truck, you can derive the speed of the flow in that particular location. And then if you, for instance, look at the mean flow, we can identify what are the main structures that are due to this, they are created within the flow you are looking at. So for instance, this is our wake, and we have the primary bubble on the top and a second bubble on the bottom. And then one last slide about the experiment. Obviously, to run an experiment like this, what you need people and you need support. And we have an excellent support from our technician team, which they come with different expertise. So you have someone that is helping making the model and manufacturing different part. You have someone that is more expert in electronics, and you've seen how much electronics we have. Then obviously we have the researchers that are first involved and make the project real. And finally, we have the people in the wind tunnel that are making sure that the facility is up and running and that is always up to date with new technology, and everything works when it's needed. And with this, I'm going to move to my last few slides about result. Obviously, the way the project is structured is that we start with a baseline characterization, trying to understand the flow physics and what the wakes look like. The second part has been a static optimization of the flap angle and length. And then I will show when the reinforcement learning take over. So this is the wake behind the track that I was showing earlier. And for instance, one thing we can do is that we can compare what happened when the rolling rod is off respect to the rolling rod is on. And this is quite important for us because we can't always keep the rolling rod running. But you can see in this case that the effect of the rolling rod, so we have these vortices in the wake A, B, and C here on the top. And you can see that the effect of the rolling rod is a bit limited, is more limited to the region next to the ground. And then we put our flaps that are static, and again we can have a look at how the wake is modified by the flaps. And first things that comes to eye is that now the wake is more elongated, and the vortex here that was on the bottom, which was B, has now disappeared. And these are all elements then with a bit more deeper analysis that what I'm showing now will guide us towards the understanding of why already static flap can reduce the drag. Then we can move to the static optimization, and the idea is now, okay, what if instead of keeping these flaps at 0 degree angle, we want to optimize their angle? If you have a vehicle that is straight to the direction of travel, then we can do a simple grid search. So what we did is moving the angle by a 0.5 degree every time, and then we studied 4 different lengths. And what we found is that the actual force, the actual drag force, is reduced by more than 20% with in the best configuration, which obviously is the one with the longest flap and a certain angle 1.5. Instead of moving each step with a fine resolution, another possibility is to work on optimization code. And what we tried was the Bayesian optimization, and the square in this plot shows the result on the static optimization for like the straight track. And then what the Bayesian optimization becomes even more important when you actually want to study the yaw condition, because in this case, the optimal is not necessarily that the two flaps are set at the same angle, but they actually can be optimized independently. And what you have is a number of points that are randomly chosen to start collecting a data set based on which the algorithm will then decide the next step to optimize this function. And we can see in this case that if we compare to the 0 degree case, we can get a drag reduction. So instead of if we would keep the flap straight at 0 degree, if we now put the optimal angle, we will increase even more at 1.3% of drag. And this is a small yaw angle. When we increase the yaw angle, the increment that we can have with an optimized angle at yaw is actually much higher. But what I mentioned earlier is that if we look at the flow in the wake, well, it's the flow in the wake is quite dynamic, it's not static, and we do use a lot of analysis like PSD or POD to understand how this dynamic part of the wake is contributing to the loss of energy. And this is because what we were really to understand is which are the most energetic structure. There will be those that we want to control. So when we look at the dynamics of it, how can we now make the flaps moving in a way to actually optimize the flow, like to optimize to reduce the drag? Well, in this case, we said we want to use a feedback control. So our sensor, the first question is where can we place the sensor? Obviously, we cannot place a sensor in the wake of the track that is following a truck moving on a road. But we need to mount the sensors on the vehicle. So in this case, the first question that we have to pose is observability. Can we actually use this sensor to be able to observe the state of the wake? That is what we want to control. And actually the base pressure on the rear of the vehicle, as I shown earlier, is a good indication of the state of the wake. So we use pressure transducer on the rear face of the vehicle. Then we want to measure the drag, and for that we use the load cell. And our actuators are obviously our motors that need to be fast enough to be able to respond. They need to be fast enough to be able to control the wake. And also our communication needs to be fast, so we use a real-time communicator. And we have a parallel computer in which is running the reinforcement learning algorithm. So our real-time communicator is sending the observation to our computer, and the computer is returning the next action, which eventually is fed to the actuators. A bit more into detail of how this works. We have, in terms of reinforcement learning algorithm, we have our wind tunnel, which is obviously the environment, and the state of the wake, which is measured by this pressure transducent, and the agent will decide which action to take at a certain distance of time, which will be how these flaps needs to be moved. This information is fed back into the environment, and eventually, if the effect is positive, reward will be an according reward will be sent back to the agent, and they will decide what the next action. And the way this works is that it's divided into 2 steps. One step is training, one step is evaluation. So in the first step, the algorithm trains itself, and then he confirmed that during the evaluation state, it observed what the training has suggested. So this is one image that shows how the algorithm works. It's getting a bit more complicated, but what I'm showing here is a power. This basically energy as a function of Stroll number, which is a different frequency in the flow, and this is from the pressure signal on the rear of the truck. So you can see the black curve represents the uncontrolled case, the baseline, and these peaks are the frequency that contains more energy, so those that we want to reduce. And when we start, the red curve is the control. So if I now start this video, you can see that after a few episodes of the controller in action, the red curve is becoming lower than the black curve, and this means that it will contain lower energy, and eventually it reaches a steady state. Now the different strategies can be tested, and this is something we've been working on, whether you want to use only the left and right flap or only the bottom flap. And when you start doing this type of experiment, you can actually observe what we call different mode in the wake, so different structure that you are actually, different state that you are actually controlling. And depending whether you're using the left and right or the bottom flap, for instance. So there's also an element of learning from the agents, learning something about the flow and how you can control the flow. And with this, I think I getting to the conclusion of my talk. Just one slide. Obviously, there are more experiments that will be carried out to develop the algorithm further. We have one experimental session starting on Thursday, in which the idea is that all the 4 flaps will be controlled together, and also the effect of, we will also investigate the effect of variation in the mean flow. For instance, what happened when we change the wind direction. And then the next step of this project will be always obviously start looking at real scale proof of concept, because scaling these things are not obvious. And we also would like to obviously see this in technology implemented on real track in the future. We wish that, and obviously there are a lot of practicalities that needs to be addressed. And finally, what is the future of the algorithm? Because it's what we learn by optimizing the flaps behind the track is obviously coming very useful for different aerodynamics problems. So we are looking for the next application. And with this, I'm going to conclude. And thanks for the presentation, the attention. And these are the people that are working on this experiment. So Rodriguez that came up with the, it's obviously the PI on the project. And then we have Shenzhen Zhang, Max Weisenberger, the Anton Plaksin, and Shen Weixia and Shunxin Zhang that are PhD students working with. And thank you.
Thank you for your presentation, Isabella. That was so great. So for the sake of that, we have time for some few questions. Ahmed, if you have any question, please.
Yeah, thank you, Isabella, for the very interesting talk. If you recall, we had a session before when the voice was not working. I am really impressed with that you took all the link from experiment to couple it with reinforcement learning and troubleshooting all the way. I'm sure that troubleshooting in real life is much harder than hyperparameter optimization for a machine learning model. That's more challenging. So it's very impressive work. My question about here comes to the value of information from the pressure sensor. In my group, we have tried to work on like drag reduction around the cylinder, and we are doing it only numerical studies. So the benchmark is usually puts a lot of pressure sensors in areas where we can't measure. It's just for your example will be like 10 meter after the end of the truck, and this is where actually the information is highest if we comes closer. So what is your perspective, how to maximize the value information with the constraints of real life?
Yeah, I mean, it's a good point, actually. We are planning on doing some tests with a pressure rake on the back of the truck to compare what would be the result if you had direct wake control respect to indirect one. Obviously, we have I think we have a setup in which we are quite lucky of being able to observe some of this dynamic on the rear of the truck, like having localized pressure sensor. But yeah, this is a really important aspect when we do this type of research, is because if you want to move to real life, you can have pressure sensor, I believe, but you can't have something downstream. So obviously the indirect observation, you're always missing something.
Fair enough. And that comes into working in uncertain environment. If we have very few observation or uncertainties in the direction of the wind in real time, we have seen yesterday there was an accident of an aeroplane in Toronto, and people are guessing was there's gust pushing it down and pushing it towards the landing, so it crashed faster than usually, or was it the estimation of the height? But the human intelligence usually somehow, most of the time, predict or react instantaneously to uncertainties in more conservative ways. Do you think that the reinforcement learning is able to learn similar patterns?
Yeah, that's what we want to investigate, actually. When the idea is if you're training in a certain condition and then you have a condition change, can you still be able to cope with it? And I guess that is the final part of our task, really, is and it becomes a bit more complicated because you need the substantial training, but probably I think it can help in that circumstances as well. I mean, in the future, obviously.
Fair enough. So I don't have any further questions. Let's check if we have comments coming in from the YouTube channel. We don't see any other questions. Amin, the last question is for you, if you have any.
Yeah, sure. Yeah, because we don't have really much time. Could you explain briefly about your agent model and what is your agent and how these agents work?
Well, I would rather I would probably pass this question to people that are more expert than me in the project, because I don't want to shame the basically the people that have worked on the algorithm are like some of the people I've shown in the pictures. I don't want to
Makes sense. Yeah.
say something that.
Okay, that's fine. Yeah. Please.
No, I think I think for the sake of time, we have now at past 30 minutes, half the hour. So thank you, Isabella, again. And as I mentioned, this is the second time to give the talk. The first time we had the technical difficulties for the voice. So thank you for volunteering to speak as the webinar series again. I really appreciate committing the time, and looking forward to see the rest of the results of your exciting project.
Thank you.
Yeah, I will remove the banner now and hand back the chairmanship to Amin to introduce the second speaker.
Well, thank you again, Isabella, for your presentation. Our next presenter is Meshkat Dolat from University of Saudi. The brief bio from Meshkat's background is he's a third-year PhD candidate at the University of Saudi at Department of Chemical Engineering, with a strong industrial background in the oil and gas and energy sector, as well as academic credentials, including undergrad in applied chemistry and chemical engineering from BIHE in Iran, and then Master of Science in Process Integration from University of Manchester. Meshkat is a specialist in process design, optimization, and carbon capture technology. His PhD research focuses on advancing dual function material reactor technology for carbon capture and utilization, while their role as a research assistant involved optimizing anaerobic digestion for enhanced sustainability and efficiency of biomethane production. Today, he has a talk under title of the Anaerobic digestion feedstock acquisition under uncertainty and scheduling optimization with dynamic demand. Thank you for joining, Meshkat, and the floor is yours.
Meshkat, may I ask you to share your screen again because you stopped the sharing?
Oh, sorry. So
no problem. Take your time.
I'll share the entire screen. Hopefully it will be all right. And
can you maximize? Yes. Can you? Yeah, if I assess it. Okay, thank you. The floor is yours again. Thank you, Meshkat.
Yeah. Thank you very much. Yeah, thanks for the introduction. Yes, my name is Meshkat Dolat, and today I will be presenting my research outcome in the field of anaerobic digestion, feedstock acquisition under uncertainty, and scheduling optimization with dynamic demand. Actually, my research is part of a larger project, AI for AD, which aims to develop AI tools to achieve transformative efficiency improvements in the AD processes. So, as you may know, current AD processes face challenges due to limited flexibility and the predictability, and also this causes so many difficulties, and it's primarily resulting from the inherent complexity of the microbial interactions under varying operational and feedstock conditions. In addition, feedstocks availability as well as uncertainties related to gas demand and market prices impose significant challenges to these kinds of processes. So these factors highlight the need for more rigorous scheduling approaches and like predictive tools to improve decision-making processes in these kinds of industries. So actually, my work, which is the first work package of the whole project, can be categorized in two phases. In the first phase, I've developed a platform that takes into account different feed characteristics and properties such as locations, availability, weights, the seasonality, and also different substrate characteristics and GWP factors, etc. And this platform operates under two consecutive functions, which one of them is co-digestion, and the second is the scheduling. So co-digestion calculates the biomethane yield due to some synergistic effects. And the scheduling actually takes all the data from the feed and co-digestion function and suggests a feeding pattern that matches the future gas price. So the platform assess the effectiveness of gas storage in terms of flexibility and adding to the profitability of the plant. So all these features are kind of the elements that we've incorporated in this platform to enhance the decision-making process. So looking back at the co-digestion function, actually this co-digestion function is written in Pyomo and follows a nonlinear programming style. The model is based on surface response model that computes the optimal blending recipe according to the model which is proposed in a reference work. And the objective is to identify the optimal feeding ratio that leads to the highest biomethane yield. So the platform actually allows the substitution of the aforementioned surface response model with actually AI models, provided accessing to sufficient amounts of microbial community and growth data. So what I need to emphasize is that I've developed, in this work package, I've developed a scaffold for integrating the AI tools in the anaerobic digestion optimization and decision-making process. So the next function, which is the scheduling, is written as MINLP. So the biogas production models is currently utilize a simple mechanistic model, and the price prediction is based on some fixed parameters and assumptions now. However, they will be both replaced by, again, AI algorithms trained on bespoke set of data sets for each 80 plants. So depending on the 80 plants, depending on their bespoke conditions, reactor size, and feedstocks, the AI tool will be able to be trained to yield set of bespoke trained models that can be fully integrated into these kinds of platforms and enhance the decision-making process. For evaluation of the model and validating the results and kind of usefulness of the model, we did a case study. So this study covers 3 different time periods of natural gas price fluctuation, which we categorized as low, mid-range, and high-range prices. These prices were actually determined according to the Ofgem from February 2021 to February 2024. And feed data were acquired from project industry partners such as Exera Energy and Future Biogas. This case study actually takes into account different scenarios for availability and seasonality of the feeds, and is based on a farm scale AD plant. So here are the results from the co-digestion function. This graph actually illustrates the distribution of cost and biomethane potential for different feed blends. For this example, is a 2-component system. So this actually is resulted from this co-digestion function, and specifies the changes to the biomethane potential of each blending recipe and its contribution to the cost. So ideally, we're looking for feed blends with maximum biomethane and lowest cost per weight of the blend. Now here you can see the optimization results and the suggested schedule for the predicted gas price in low frequency zone, for example. The top one actually shows the optimal schedule and production profile without taking into account feedstock acquisition and GWP effect. While the one at the bottom shows the effect of inclusion of the GWP. So at this stage, no on-site storage has been considered for the results, and you can see the adaptability of the production to the demand. However, it is limited due to the low flexibility nature of the AD process, which is usually running on relatively high solid retention time. In this slide, you can see the effect of manipulating the grid supply by the aid of mass storage facilities, which here is actually the cryogenic cycles. So we're using the cryogenic processes to mass store something like 10,000 cubic meter of gas per day. So as you can see, the revenue out of this manipulation of the grid supply has increased by 40,000 pounds annually in the low frequency zone, in the lowest possible fluctuations of the prices of the gas. Now, if we move forward to other price zones, such as medium or high frequency zones, these are the prices that has been, let's say, experienced in different intervals. So as you can see, inclusion of the mass storage facilities can earn up to more than 300,000 pounds a year, which is massive. So in terms of the storage and inclusion of bio-LNG and cryogenic cycles, we need to say that large storage of methane for price matching and grid supply optimization has been achieved through these liquefaction cycles. And at the moment, we need to pay attention to the fact that the currently biogas upgrading processes use membrane filters, which do not let us the CO2 storage possibilities. Now, with the inclusion of the liquefaction cycles, we can perfectly facilitate this separation of the carbon dioxide from the biogas and store them in a liquid form or in a gas form, whichever is convenient for us. So we assume extra revenue can be achievable through these kinds of processes, so that we can, let's say, liquefy, store, or ship these captured carbon dioxide elsewhere and earn more revenue because of the carbon pricing schemes. Now, for the second phase of this project, we focused on feed acquisition and the uncertainties associated with it. These uncertainties include variations in quality and quantity. By quality, I mean the crop yield, and by quantity, I mean the crop yield, and the quality is something like the total solid, the biomethane potential of different crops. Additionally, market price fluctuation under different scenarios has been taken into account. So these uncertainties are largely influenced by external factors such as weather conditions, soil quality, economic trend, etc. So actually, this creates significant challenges for decision making, as choices must be made in advance while accounting for unpredictable circumstances in the future. So a key challenge for AD plans nowadays is developing a systematic and robust approach to mitigate the impact of these kinds of uncertainties. So to address these kinds of concerns, we employ stochastic optimization to enhance decision-making process. So our approach determines optimal land allocation strategies, and we've outlined viable courses of action once these uncertainties materialize in the future. So a significant advancement in this phase is the integration of these kinds of uncertainty considerations into our previously developed platform. This enhancement incorporates co-digestion constraints, digester feeding limitations, and also variations in the gas prices, so that we could be ensured that the feed acquisition planning is both economically and operationally viable. So this two-stage optimization framework, this is a stochastic optimization framework, we have to make decisions in two steps. So in the first phase, first decisions are made before the uncertainty in crop yield is revealed. So this involves deciding how to allocate land for planting and balancing the expected costs and potential profits. So the objective here is to minimize the planting cost while maximizing the expected profit from the crop sales in future. Now, the second stage, which we call it recourse decisions, are made after uncertainties such as actual crop yields, quality of the yields, and market conditions become unknown. So these decisions allow operators to adjust their strategies to mitigate the impact of the unexpected changes, for example, by selling or storing the surplus amount of yield or externally purchasing the required feed. So the key advantage of this approach is the fact that it can integrate flexibility into decision-making and making sure that even if unforeseen circumstances occur, the system can still adapt to maximize efficiency and profitability. Now, to enhance the accuracy of the scenario planning, AI-driven techniques will be integrated into this platform. So by leveraging historical weather pattern or soil conditions, market trends, and historical AD process data, the AI model can actually generate realistic scenarios. It can predict possible crop yield and quality variations in different environmental and economic conditions, and it can continuously refine probability distribution. So in general, it can be quite adaptive and robust, which can lead to more realistic and resilient and efficient AD feedstock management and process. So here you can see a snapshot of the Excel interface we have developed for data entry and result visualization. This interface serves as the central point where operators input all necessary data. So these data could be feed properties, scenario definition, adjustments to the feed properties, and of course, these AI-powered tools will assist us in adjusting feed properties and prediction key parameters under different conditions. So once the data is entered, the Python model processes the data, and it calculates the optimal decision for, firstly, the planting stage, and then the cultivation period, and also the anaerobic digestion feeding schedule. So here you can see for example, on the right-hand side, the schedule yielded from the optimization process. So this model is designed to function after the uncertainty is resolved. So meaning that when the actual scenario is become known to us. So in this case, the optimization is reapplied to refine feeding schedules and operational decisions. And the model can adapt itself to update the gas price prediction to ensure maximal profitability under real market conditions. So this platform is actually capable of real-time operation, meaning that all linking parameters are updated with each run to ensure the latest data is reflected in the decision-making process. And we need to say that the initial land allocation decision remains fixed after the first run because it is a long-term planning choice. So I think by integrating AI, Excel, Pyomo, and these kinds of tools, you can provide a practical and data-driven decision support system for AD plant operators. So that brings us to the end. I'd like to express my gratitude to the University of Surrey and AI for AD team for the collaboration on this project. Special thanks to Dr. Michael Short for superheading this very interesting project, as well as our industrial partners such as Future Biogas and Exora. And I would like to also extend my sincere appreciation to AI for Net Zero team for providing me with the opportunity to present my work. So thank you very much, and I'm open to your questions.
Thank you so much, Meshkat, for your presentation. Yeah, we have time for some question. Since we don't have any question in chat box, Ahmed, if you have any question, please go ahead. We don't have your voice.
Sorry about that, I was muted. Thank you for the very interesting talk and for the integrated framework. So when you do the integration of this framework, there is many moving parts in my mind. Like, how do you debug this system and discover if there is all, like, I come from engineering background, undergraduate, and they used to talk about just back of the envelope calculations, and if something is not correct. When you have a framework with multiple moving parts like that, how do you tackle that?
Well, yeah, that's a good question. Actually, this is as you said, this is the main challenge for every academia working with codes and working with algorithms. So as you mentioned, these algorithms are quite different in terms of the scale of flexibility, in terms of stiffness levels. So yes, the point is we tried to tackle this problem in, as mentioned, in different phases and in some sequential approach. So firstly, we tried to separate the problem into different intervals so that we could solve them separately without taking into account the fact that this separation will lead into suboptimality. So we solved the problem step by step and then started to integrate all these kinds of formulations and model together to see to what extent the model can be integrated in a single platform, and to what extent the number of, I don't know, something like variables, the number of constraints can affect the computational time, the effectiveness of the model, and the let's say the exactness of the results.
It's very interesting that you talk about the exactness of the results, because this is the subject of my next question. When you increase the number of uncertain parameters, what is the notion of exactness here? What is the impact of that on, do you reach a good optimum solution? Like how do you, so do you slow the learning because of that, but then the expected improvement is lower or higher? You escape local minimum. What's your experience with this dilemma?
Well, it's a very good question. Actually, as you may know, this kind of uncertainty and optimization under uncertainty is quite very much relies on the fact that how well we have designed and crafted our scenario generation and probability distribution. So the main challenge is actually having a platform which actually takes into account decent, let's say, scenarios and decent probability distribution. So this is the actually the bottleneck of your question, I think. So as I mentioned, these kinds of processes can be enhanced by utilizing the AI-driven and data-driven tools. So based on historical data and based on some real prediction tools, real-time prediction tools, I believe that this is the maximum that we can get out of it. So because the prediction is actually the challenge. Having the newspaper for tomorrow's newspaper is actually the key here. So, but I believe that as we proceed, as we moving forward, there are more robust AI tools being introduced to the market that are capable of predicting future in terms of being trained on historical data and sometimes being coupled with some mechanistic model so that they can predict better and better the future conditions, and they can better give us the distribution of the probabilities for future. So I believe these are in the area of the AI driven tools, and the extent of decent operation of these kinds of tools, depending on the data sets under which they're trained, and the scenarios that they generate. So this is just a scaffold. So depending on the scenario and depending on the decency of the scenario, it will give you the better result, or else.
Fair enough. Thank you for the answer. I don't have any other question.
Yeah, there is no question in QA box, but I have some questions, some small question. I know it's little bit out of time. But do you have any cases, or do you know any cases from real world storage, LNG storage incentive and application of that?
Well, recently we were approached by SGN. For example, I know the government of Scotland is planning to test the flexibility of relying on renewable sources. So nowadays, what I know is they're trying to start some biomethane islands, which means that they're trying to be isolated from the grid, and they need to rely only on renewables coming only from AD plants. So as you can see, and as you can imagine, these are kind of very huge plants in the future, one of the largest of their kind. And so the flexibility becomes the main issue for these kinds of processes. So we can imagine some times of the year that there are surplus amount of gas generated, and there are some periods in the year that we are facing challenges in terms of the gas deficit and network deficit. So I believe these kinds of processes, these mass storage facilities, will come to play in these kinds of conditions. So during the time that the demand is low, I think that the gas, the biomethane that's produced in these kinds of processes will be stored. So LNG is the only option that we have, because, for example, imagining a very small scale, farm scale AD plant, it produced something like 10,000 cubic meter around it, 10,000 cubic meter per day. So it is a huge amount of gas to be stored in strategies such as the pipe looping and pressurized storaging. So the only solution to this would be the LNG. And taking into account the fact that by LNG we can be offered the possibility of separation of the CO2 and storaging it, and utilizing it in other processes. So I believe this would be a very interesting and promising future in this field. And yeah, we'll see how we can be applied into real conditions.
That's great. Thank you, Meshkat. Thank you for your presentation and your answering question so completely. Because we have a little bit out of our time, I would appreciate all audience to stay with us until now. And Ahmed, if you don't have any other words, so we can have a goodbye and see you for the next session. Thank you for all presenters.
Amin. So I would thank the speakers again, and I would like to announce the next webinar for next week, next Tuesday, the 25th of February, at 2 p.m. GMT time, as usual. We will host Dr. Hussein Mohammadi from the University of Exeter, and he will give us a talk on the sequential adaptive design for emulating costly computer codes. So please join us for this exciting and timely talk. Thanks again to Isabella and Meshkat and for their informative talks, and for Amin for hosting this session, and looking forward to see you next session. Goodbye.
Thank you.
Goodbye.
Goodbye.